Hey, let's talk about time dilation. So time dilation is a very interesting topic. What you see here is a fully worked out problem, and we're going to show how to work out problems with time dilation. But first let's talk about what time dilation is and where we got this idea from Einstein. So let's start out with what's known as the twin paradox. So the twin paradox asks the following question. If you've got two twins, we've got Benny and Jenny, both 20 years old. Benny's going to stay on Earth, Jenny's going to travel at 99% the speed of light to Proxima Centauri, which is about 4 light years away, and then travel home at the same speed. And the question is, how old will each twin be when Jenny returns? So, for Benny, the calculation is pretty straightforward. He's moving at, she's moving at almost the speed of light. So if it would take 4 light years to get there, that means 4 years time for light to get there and then 4 years back. But because she's not quite moving at the speed of light, she's only 99% of the speed of light, then for Benny it will seem that she came back 8.1 years later, or he'll be 28.1 years old. And the question is, when Jenny returns to Earth, how old will she be? And it turns out that she's going to be 21.1 years old. Now you must be looking at this and scratching your head and saying, how is this possible? How is it possible for two people to measure time completely differently? Benny measured 8.1 years of time and Jenny only measured 1.1 years of time passing. This is the result of time dilation. And time dilation is not just a theory, it's a proven consequence of special relativity. So it's so real that every time you use your phone to access location data with Google Maps or Apple Maps, you're using time dilation to triangulate and pinpoint exactly where you are. So this is a very real consequence. So just to do an overview of Einstein's theory of relativity, there's two branches. There's special relativity and general relativity. We're going to focus on special relativity, in particular time dilation. And the big questions in special relativity are, how are time and distance distorted when objects travel very fast? General relativity explores what is gravity. Okay? So the applications of special relativity would be time dilation, length contraction, the energy mass equivalence, E equals mc squared, and nuclear reactions and nuclear energy. Whereas for general relativity, we're talking about gravity as warping the four-dimensional space-time fabric, gravitational waves, gravitational lensing, and black holes. So let's go ahead and get into our theory for time dilation. And in particular, we're going to start out by looking at the two postulates of special relativity. Now, a postulate is simply an assumption that you make when you come up with a theory. So Einstein's first postulate was that the laws of physics are the same in all inertial reference frames. Now, let's unpack this a little bit. Let's remember what a reference frame is. A reference frame is any coordinate system. So a soccer field could be a reference frame, a classroom, a train, a plane. Even if they're moving, they could be a reference frame. And Earth could be a reference frame as well. Now, what do they mean by inertial reference frames? The word inertial in this context means not accelerating. It means constant velocity. So any inertial reference frame would be a constant speed of a bus, a constant speed of a spaceship. That would be an inertial reference frame. Let's talk about what's not an inertial reference frame. Because the postulate was that the laws of physics are the same in all inertial reference frames. So what if we had a bus that was slowing down? If you had a tennis ball on the floor of that bus and it was moving at a constant speed, you would expect the tennis ball, except for any bumps in the road, to stay relatively in the same place. But once the bus hits the brakes and it starts to slow down, you're going to see, of course, that tennis ball starts to move towards the front of the bus. Now, Newton's second law states that for any acceleration that you observe, there should be a force causing that acceleration. But there's no force magically acting on that tennis ball. We know that the tennis ball has inertia. From your point of view, from your reference frame on the bus, it appears that the tennis ball is accelerating with no force acting on it. And therefore, Newton's second law is violated because the bus is accelerating. It is not an inertial reference frame. So the laws of physics are the same in all inertial reference frames. But once that reference frame starts to accelerate, the laws of physics can change. So he says, well, look, as long as we're in inertial reference frames, the laws of physics have to stay the same. Okay? The next postulate is this. The speed of light in a vacuum will be measured exactly the same in all reference frames. So regardless of how fast you're moving, you're always going to measure the same speed of light. And this was actually predicted by Maxwell. Maxwell said, when he did his calculation for the speed of light, he said, this electromagnetic wave has to move at c equals 1 over the square root of epsilon naught times mu naught. Now that's not dependent on the speed of the source, the speed of the observer. It's just like, look, this is how fast the speed of light has to be. So these are the two assumptions. And based on these assumptions, we're going to build the whole theory of time dilation. One thing I want to share with you is that a single event can appear different in different reference frames. So, for example, when we were studying two-dimensional motion, we explored the case where a car passenger might be traveling at 65 miles per hour and he tosses an apple straight up. If you're in the car frame, so in the car frame, what are you going to see? Well, you're going to see that apple go straight up and come straight down. So if I use this roll of tape as my apple here, I can throw it straight up and it comes straight back down, right? That's my apple. And even if I'm moving at 65 miles per hour, if I toss that apple straight up, it's going to come straight back down. So from the car frame, what you see is the apple go up and come straight back down. So straight up, oops, straight up, and then straight down. But what about in the road frame? If you're an observer on the side of the road, what do you see? Well, the car is going to be, let's say, at 3 locations. Here's the first position of the car, here's the second position of the car, here's the third position of the car. So the apple is going to start in the hand of the passenger. So here's the apple here. It gets thrown upwards, so it reaches the top of the car, and then it comes back down and it reaches back to where the person threw it. So we know that it follows this parabolic trajectory because it was given an initial vertical velocity, but the car was moving with a horizontal velocity, and under the influence of gravity, it follows this parabolic trajectory. So in 2 different frames, you're going to see a different motion, even though it's the same exact event. This is the basis of our derivation for time dilation. Okay? So let's go ahead now, and let's move forward, and let's really get down to our derivation of time dilation. Now this is specifically called velocity time dilation. There's a different kind of time dilation called gravity time dilation, but we're going to focus on velocity time dilation. So we're going to start with a definition of a light clock. Now, before I define to you what a light clock is, let me show it to you. The best way to illustrate something, I believe, is to show it to you. So give me a moment to pull this up. Okay, so what you have in this YouTube video is a light clock. Now, notice what the light clock does. It shoots a beam of light upwards, it hits a mirror, and then it reflects off the mirror and comes back down to the detector. This detector down here is going to measure when the light returns. Okay, so it's called a light clock because the light goes up and it comes back down, and we measure the time that it takes for the light to go up and then come back down. And you can see that this light clock kind of works like a grandfather clock, moving backwards and forwards and measuring the time that it takes. So if I were to represent this in a diagram, I would represent it like this. I would say, okay, the light clock measures the time for light to travel a given distance. We're going to have a source, which we represent with the letter S. So S is the source, and D is the detector. So we got the source and we have the detector, and we fire the light up, straight up. It hits up here a mirror. So here's our mirror. And then once it hits the mirror, it goes up, hits the mirror, and it comes straight back down. Okay? We're going to call this distance here D. So now we're going to take a light clock and we're going to put it on a spaceship. Okay? So consider a spaceship moving at speed v. So here's our spaceship, here's our velocity vector, it's moving at speed v. Now, we're going to start out inside the spaceship. Inside the spaceship is what we call the rest frame. And the reason we call it the rest frame is that the clock is going to be at rest relative to the frame. So if we're inside the spaceship, the clock is at rest relative to the frame, okay, relative to the spaceship. So what are we going to see inside the spaceship? It's the same thing if you take the apple and you toss it straight up. You're going to see that apple go straight up and come straight back down. So inside the spaceship, we've got our light clock. So here's our source. Here's our detector. So we go up a distance d, we come down a distance d. Okay, and here's our mirror right here. Okay, so let's go ahead and let's solve for this new quantity that we're going to call the proper time. Okay, the proper time is delta t naught. Now the official textbook definition is a little bit strange, so let's unpack it. It's the amount of time separating two events that occur at the same location. Now when the photon is released, when the light beam is released, and when it's received and detected, that's still at the same location. It's still inside the spaceship. So that's why we call this the proper time. But for our purposes, the easy way to remember the proper time is that it's the time measured by the moving object. So I like to think about it in terms of a tea party. I picture a British tea party going on inside this spaceship, and everybody's sipping their tea and they're all dressed all fancy. And it's called the proper time because everybody's acting all proper and dressed all proper. Okay, so the proper time is the spaceship time. It's how much time is measured inside the spaceship. So what we want to do now is calculate this proper time based on the speed of light and based on this distance d. Okay, so we're going to say, all right, delta t naught is going to be equal to the time for light to travel. How much distance? Well, the light has to go up a distance d and come back down a distance d, so the distance has to be travel a distance 2d. Okay, so if we want to solve for this time, let's start with the equation. Speed is distance divided by time. Okay, in this case it's the speed of light because light is traveling here, so we're going to say c is the speed of light, is the distance, well d plus d is 2d, over this amount of time, delta t naught. And so if we solve for delta t naught, we get delta t naught equals 2d over c. Okay? So this proper time measured inside the spaceship is 2d over c. So please put this in a rectangle, please star it, please smiley face it. We're going to hold on to this and use this later in our derivation. Okay? So now we've taken care of inside the spaceship, now let's go outside the spaceship. What are we going to see if we're outside the spaceship? Now, once again, I think the best way for me to illustrate this to you is with a simulation. So let me show you what you're going to see outside the spaceship. Okay, so let's pull this up here. Outside the spaceship, now you see what we see outside the spaceship. There's the same exact light clock outside the spaceship, but now the spaceship is moving to the right. So when the light is released, the light has to move in the forward x direction while it moves up in order to keep up with the mirror. So from the perspective of somebody inside the ship, all that happened was the light went up and came back down, but the ship was moving forward. So if you're outside the spaceship, this is what you see. You see this diagonal path taken by the light. Okay, so we're going to see that reflecting now to come back to the detector. And once the detector receives that photon, that light, it's going to shoot a photon back. And so you're going to see this zigzag pattern of the light as it goes up, hits the mirror, comes back down, and then is released again. All right? So outside the spaceship, this is what you see. So if we go back to our notes, let's try to unpack this a little bit further. Outside the spaceship is what we call the inertial frame. So the word inertial in this case means not moving. So let's say that you've got a planet. That's going to be a good inertial frame relative to the spaceship. So the spaceship's moving very fast. The planet will be relatively stationary in this frame. A star could be an inertial frame. An inertial frame is simply outside the spaceship, somebody that's not moving, okay, relative to the spaceship. All right? So what we want to do is we want to unpack the diagram that we just saw. So if we take a look at this diagram, we're going to say, okay, let's draw the light clock in 3 positions. So here's our source and our detector, here's our mirror, and then we're going to draw another source and detector and our mirror, and then another source and then detector, and then our mirror. Okay, so as we saw in the video, the light is going to travel along this diagonal. It's going to hit the mirror, it's going to bounce off, and get detected over here. Now, because this spaceship is moving with speed v, we can say that this distance from here to here is going to be, distance is velocity times time, right? So we're going to say that this distance is the velocity v times the time that it takes to get from point A to point B. Well, we're going to call that time delta t. So this is v delta t. Now, what about the time that it takes to go from the first location to the midpoint? Well, if that's exactly half the distance, then that will take half the time. So we're going to say, okay, this distance here to the midpoint is going to be the speed v times delta t over 2. Now, this height for the light clock we had called d earlier, right? So that distance is d. Now we want to look at what this hypotenuse distance is. Well, what is moving along the hypotenuse? It's not the spaceship, it's the light. The light is moving at a speed c times the time that it takes for the spaceship to reach this midpoint. Well, we said earlier that that would be delta t over 2. And so now what you might notice is that we have a right triangle here, and with a right triangle, of course, we can use Pythagorean theorem. So let's go ahead and use Pythagorean theorem to set up this problem, and ultimately we want to solve for this delta t. Okay? So, if we set this up, we're going to say, okay, a squared plus b squared equals c squared. So v times delta t over 2 quantity squared plus d squared equals c times delta t over 2 quantity squared. Okay? Let's multiply this out. So v squared delta t squared over 4 plus d squared equals c squared delta t squared over 4. Now let's subtract this v squared t squared over 4 term from both sides, and let's write the c squared term first. So we're going to write c squared delta t squared over 4 minus v squared delta t squared over 4 equals d squared. Now let's get rid of these 4's by multiplying both sides by 4. So we're going to get c squared delta t squared minus v squared delta t squared equals 4 d squared. And now let's go ahead and let's factor out this delta t squared. And we're going to get delta t squared times c squared minus v squared equals 4d squared. And let's divide both sides by the c squared minus v squared term. So that's going to yield for us, I'm going to move on to a new paper here. So if you need to catch up, please pause the video to catch up. We're going to have now delta t squared equals 4d squared over c squared minus v squared. We're going to go ahead, we're going to square root both sides now, and that's going to give us a really interesting result. Delta t is going to equal 2d over the square root of c squared minus v squared. Now you might notice that we're really close. If you go back in your notes a little bit, you might notice that we're really close to what was called the proper time. Okay? We said that the proper time was delta t naught equals 2d over c, right? Well, we're very close to that 2d over c. So let's see if we can get a c out of this denominator. Let's go ahead and let's factor out a c from this term here. So 2d times the square root of, let me take out a c squared. Let's see what happens. If I take out a c squared from this denominator, I'm going to have 1 minus v squared over c squared. Does that work? Check it out. C squared times 1 is c squared. C squared times v squared over c squared, well, the c squared will cancel and leave you with v squared. So yes, it does work. Very nice. So now, what we're going to do is we're going to take that square root of c squared, and we're going to be left with 2d over c times the square root of 1 minus v squared over c squared. Now, if we rewrite this as follows, 2d over c times 1 over the square root of 1 minus v squared over c squared, now you can see that this 2d over c that we early defined as the proper time, delta t naught, that can be substituted in here. So this is going to be delta t naught. So when all is said and done, when the dust clears, this is what we have. Delta t is equal to, in the denominator we have a delta t naught. I'm sorry, in the numerator we have a delta t naught. In the denominator we have a square root of 1 minus v squared over c squared. And let's put a rectangle around this. Let's star it 3 times. Let's smiley face it, because this is a big deal. What is this quantity here? What is this delta t? It's so special that we really have to unpack it. Are you ready? But before I unpack it, I want to say something to you. I want to say that for all speeds v greater than 0, so as long as you're moving, as long as the spaceship is moving at all, this fraction, v squared over c squared, is going to be less than 1. Okay? Because the speed of the spaceship can never reach the speed of light. Okay? That's one of the understandings of special relativity that we're not going to prove right now. But let's make the assumption that you simply can't travel faster than light. Then that means that this fraction, v squared over c squared, will be less than 1, right? And then if you look at the fraction 1 minus v squared over c squared, if you take the number 1 and subtract a number less than 1, you're going to get a number less than 1. So 1 minus v squared over c squared will also be less than 1. For example, if v squared over c squared happen to be 1/4, if you do 1 minus 1/4, you get 3/4, and that is less than 1. So now we have a denominator that's less than 1, because the square root of this 1 minus v squared over c squared is also going to be less than 1. Because if you have a number less than 1 and you take the square root of it, that number will also be less than 1. Which means that there's a very important relationship between delta t and delta t naught. Okay, this is of course the proper time over here. If this denominator is less than 1, ask yourself this: what happens if you take a number, in this case the proper time, and you divide it by something less than 1? What are you going to be left with? Anytime you divide by a number less than 1, you're going to end up with a number bigger than what you started with. So that means that this time here, which has a special name, which we're going to go over in a second, is always going to be bigger than the proper time. This delta t is so special that let's take a moment and let's talk about it. Delta t is, first of all, as we said before, is the time measured outside the moving object. Okay? It's also called the time measured in the inertial frame. So if you're on Earth or if you're orbiting a star, you're in the inertial frame, and so you're going to measure this delta t. Well, this delta t has a special name. It's called the dilated time. And the reason it's called the dilated time is because we just proved that this delta t will always be bigger than the proper time. So outside the spaceship, you always measure a bigger time than you would measure in the spaceship. That's why it's called the dilated time, because the dilated time, dilated means bigger, right? Dilation is to get bigger. That means delta t, this outside time, this inertial time, this dilated time, is always greater than delta t naught, than the proper time. And that's why it's called the dilated time, okay? That's a huge, huge observation. So what does that mean in practical terms? An inertial observer, let's say on Earth, will always measure more time passing than a moving observer. This goes back to the twin paradox. When Jenny came back from her trip, Benny had measured 8 years passing, whereas Jenny had only measured about 1 year passing. This is consistent with this observation. And the faster you travel, the less time passes for you than for an inertial observer, and the more slowly you age. So you saw that Jenny only aged 1 year during her trip, whereas Benny aged a full 8 years. So this is the derivation that shows these biological aging effects of time dilation. Okay, let's finish things off here by looking at an example. A spaceship passenger travels at 93% the speed of light and listens to a 3-minute song. The question is, how much time passes on Earth during this time? So this is a typical example. This is the time measured inside the spaceship. So if you're in the spaceship, you're having your tea party, you're measuring the proper time. Okay, so we're given, in this case, the 3-minute song. That's your proper time because that's measured inside the spaceship. So delta T naught is going to be equal to 3 minutes. Okay, what else can we say here? The speed, v, is 93% the speed of light. We write that like this. We say 0.93, because that's the same thing as 93%, times the speed of light. That was easy. So now we're going to set up the equation for time dilation, because we're trying to figure out how much time is measured outside the spaceship. So we're going to say, okay, delta t equals delta t naught divided by the square root of 1 minus v squared over c squared. So now making our substitution, delta t naught is 3, that's in minutes. So if you want to put the minutes there, you can. Divided by the square root of 1 minus, okay, 0.93c quantity squared over c squared. And when you simplify this, in the numerator we still have the 3 minutes, divided by the square root of 1 minus, check this out, 0.93 squared c squared over c squared. Now you might look at this and say, oh my gosh, there's so much going on here. But don't panic, because what happens to the c squares? The c squares cancel out. And so if you put this in your calculator, 3 divided by the square root of 1 minus 0.93 squared, you will get, drum roll please, 8.16 minutes. So in the time that it took for the person on the spaceship, let's say Jenny was listening to a song 3 minutes long, Benny on Earth would have experienced the passage of 8.16 minutes of time compared to the 3 minutes on the spaceship. So this is a typical example that you would see for time dilation, and one of the tricky things with time dilation is to decide which is the proper time and which is the dilated time. If you remember that the proper time is the tea party on the spaceship, whatever's moving measures the proper time, and if you remember that delta t, the dilated time, is measured outside the spaceship, let's say on Earth, then you'll be okay. Thanks for watching, and I hope this helps, and see you next time.